Welcome back. Now we're going to talk about surface integrals. What is a surface integral? Well, a surface integral is a 2D extension of a line integral or a path integral. So essentially, instead of integrating along a curve, a path, or a line, we're going to be integrating across a surface. So we've got a couple of different things. We can integrate a scalar function over a surface. So an example of this might be integrating mass density function on a surface to find a total mass. And this idea, or this form, corresponds to line integrals of scalar functions, which we defined previously in this unit. And this can be used to, say, find the mass of a thin wire. So that's one use for surface integrals. The second form of surface integrals you might see would be surface integrals of vector fields, which again is analogous to the line integrals for vector fields we also defined previously in this section. And another example in this situation of a surface integral for a vector field would be maybe measuring the net flow of a fluid across a submerged surface, which is in that fluid, or in a sense, the flux of that field F across the curve or the surface. So that's kind of the idea of what we're doing. I know I've got the definition here on the screen, but again, I just want to reiterate some common things that we might use a surface integral for. Finding the mass of a surface, potentially finding the flow of a liquid across a curved membrane, and then also a total electrical charge on some surface. So we integrate a function over a curved surface in space as opposed to a line integral. We integrate a function over a line or a path in space. So that brings us to our formulas we have here on the screen. The formula for evaluating the surface depends on the manner in which that surface S is defined. So our surface could be defined parametrically, it could be given implicitly, or it could be given explicitly. All right, so depending on these three forms, we would choose one of these three formulas. So if we're dealing with a surface defined parametrically, and we've got that R vector, as long as it's a continuous function and it's defined on the surface, what we're going to do is we're going to be plugging in each of those components, and then we're going to have R sub u cross R sub v du dv. And you should recognize this R sub u cross R sub v du dv from the previous section. This is just the surface area differential for parametrized surfaces. So we're going to take our function, plug our components in, and integrate over the region using that surface area differential. If my surface is given implicitly, then the surface integral of some continuous function g over that surface is given by this double integral. And so we're going to take that continuous function and we're going to use that definition for our implicit surface area integrals. That would be included in there as our differential. And lastly, if the surface is given explicitly, we'll take that function, x and y, we can plug our z value in since it's given explicitly, and we use this surface area differential. So we have three different formulas that we can use for calculating a surface integral of a scalar function. And we choose the formula based on how our surface is defined. So let's look at one example. In this example, we're going to integrate the given function g, which equals z squared, over the surface, which is defined by this hemisphere, x squared plus y squared plus z squared equals a squared. And we're just saying that z has to be greater than or equal to 1. That creates a hemisphere. If that wasn't there, this would represent a sphere of radius a. Since we're dealing with a sphere, it makes sense to parametrize this using spherical coordinates. And if this is defined parametrically, then we're going to use this first formula here. So not only will we need our g function evaluated at each of those parametric components, but then we'll need r sub u cross r sub v, or the partial of r with respect to u, partial with respect to v. And of course, since we're going to define this parametrically in spherical coordinates, we're going to be dealing with phi and theta. So I won't have a variable rho. A represents some constant value. So as we parametrize this using spherical coordinates, we're going to basically go straight from our definition. So by definition, my x is going to be equal to rho. Of course, rho is my radius, so that's a. So a sine cosine theta. And y is a sine phi sine theta. And then z is rho cosine phi, or a cosine phi. So now I'm going to need to find that cross product of each of these partials. So first we'll find r partial phi. R partial phi is going to be a, the derivative of sine with respect to phi. That's going to be cosine phi cosine theta I, plus a, I'm going to have cosine phi sine theta j, and then I'll have minus a sine phi k. And partial of r with respect to theta, I've got a sine phi sine theta, and that would become negative. And then we will have a sine phi, the derivative of sine theta, that's going to be cosine theta j. And then for my k value, we don't have a theta, so there's 0k. All right, now that we have both of these partials, we need the cross product. I'm going to write that out. So using our partials, my cross product is going to look like this. So I've got I, j, k. I've got my components from r sub phi, and then my components from r sub theta. So finding the determinants of this 3 by 3 matrix, we're going to end up with I, a squared sine squared phi cosine theta, minus, remember it's always minus your j, and then we've got negative a squared sine squared phi sine theta, plus k, and this one's really long, a squared sine phi cosine squared theta, plus a squared sine phi cosine phi sine squared theta. One thing I hope you notice is we've got cosine squared theta plus sine squared theta, so factoring that out, we're just going to have that coefficient. So this will clean up a little bit, and we will now have, which looks like this. So now that we have that cross product, we need the magnitude of the cross product. Finding the magnitude is going to be each of these components squared and then summed and then square rooted, which gives us a to the fourth sine to the fourth phi cosine squared theta, a to the fourth sine to the fourth phi sine squared theta, plus a to the fourth sine squared phi times cosine squared phi. So these, we can factor that out, and we'll get a Pythagorean identity, which simplifies, which leaves us with a to the fourth sine fourth phi plus a to the fourth sine squared phi cosine squared phi. So I see a sine squared hiding in here and a cosine squared there. Factoring out a to the fourth and my GCF sine squared, that leaves me with sine squared plus cosine squared, again a Pythagorean identity. And this will just be a squared sine phi. So we need one more piece here. I need my g that was in terms of x, y, and z. I need to redefine that. So I had g of x, y, z was equal to z squared. Now, what is z in terms of spherical coordinates? Well, that would be rho cosine phi. And in this situation, our rho, the radius of that sphere, is a. So this is going to be a squared. We'll say that g of phi theta is a squared cosine squared phi. So I've got my cross product, which is part of my differential. I have g now in terms of my two new variables. And again, since rho is not variable, since rho is a constant, I don't need to say g in terms of r phi theta or rho phi theta. I can just say phi and theta because those are my only variables. So let's set up this integral. So by definition, the formula for a surface integral of a scalar function where the surface is defined parametrically, we're going to say that's the double integral of the surface. We had g of x, y, z. So this is my surface integral, d sigma. Well, we're going to redefine that, and we're going to say that's the double integral over the region, and this will be g of phi theta. And then the cross product of r phi crossed with r theta. And then we'll have d phi, d theta. So this gives us, I'm going to have, for my theta values, we'll say theta equals 0 to theta equals 2 pi. My phi value, now keep in mind we're dealing with a hemisphere, so phi is that angle off of the z-axis. So phi is going to be between 0 and pi over 2. My function g in terms of phi and theta, that is a squared cosine squared phi. This cross product, that was a squared sine phi, and then we've got d phi, d theta. So now this is pretty easy for us to integrate. I'm going to go ahead and run through that. I'm going to pull out my a to the fourth. Got my integral from 0 to 2 pi, an integral from 0 to pi over 2 of cosine squared phi, sine phi, d phi, d theta. And of course, this can be integrated with a nice u substitution. So I'm going to let cosine phi be equal to u. Working through that substitution, u squared du, negative du is sine phi d phi. My bounds, pi over 2 becomes 0, 0 becomes 1. So those are reversed. Reversing them would negate the integral, but then a double negative, basically those will cancel each other out. And now we have a to the fourth, the integral from 0 to 2 pi, integral from 0 to 1 of u squared du d theta. So this is nice and easy to integrate. I'm going to get 1/3 u cubed. So I'll say a to the fourth over 3, the integral from 0 to 2 pi of u cubed, which needs to be evaluated from u equals 1 to u equals 0 before we integrate with respect to theta. And of course, that's just going to give us a 1 in there. So I have a to the fourth over 3, the integral from 0 to 2 pi d theta, which is a to the fourth over 3. We've got theta evaluated from 2 pi to 0, which gives us 2 pi a to the fourth over 3. And that gives us the value of this surface integral when our surface was defined parametrically with respect to spherical coordinates of this continuous function g. As always, email me with any comments, questions, or concerns.